Astronomy here at the University of Iowa. We've been doing this for a while now. The show tonight is going to be concerned mainly with the tracers spacecraft launches that are going to be taking place later on this year that we have built instrumentation for in this department. What we're going to talk about is what the tracers is supposed to be looking at when it's in space. The science that it's going to do. Corey's going to introduce that. And then we are going to do some magnetic field stuff, give a little explanation of what tracers is looking for when they're doing magnetic field stuff. We're going to do some rocket stuff because, you know, it doesn't do any good if you can't get the spacecraft into space, right? And then we're also going to do some electric field and plasma stuff, because plasma is one of the things that really is what tracers is all about. So I'm going to let Corey take it from here.
Thank you, Dale. I'm Corey Stifler. I'm going to talk you through what tracers is all about here in more specifics.
All right, you have your three.
It's an acronym, and here's the main words to take away from tracers. The first one being reconnection. What is that all about? Well, the Earth is like a big magnet. In fact, it is a big magnet, big in size. It's not actually very powerful, but it's a large thing that is a magnet. The sun is also a big magnet. And these magnets, the sun and the Earth, interact with each other through, Dale called it the magnetic field. It's kind of like a magnetic wind created by the Earth, created by the sun, where these magnetic winds, fields if you will, interact. That's called the reconnection. And you see that there, the boundary of the blue surrounding the Earth, and the yellow-orange there, that of course coming from the sun. So that's the reconnection part that tracers is studying. The cusp is, you see at the north and south poles of the Earth there, you see sort of the magnetic wind sort of funneled toward the north and south poles. That's called the cusp. So that's what it is studying in particular, is the cusp. It's studying what about that cusp? The electrodynamics of the cusp. The magnetic fields, the electric fields, electric and magnetic phenomenon, and we have a lot of examples of electric and magnetic things here to show you that as well. It's doing this by having satellites up there measuring these things. What is it measuring? Well, it's measuring plasmas that are up there creating things like the aurora borealis, for example. And that's what tracers is all about. So we're going to show you some magnetic and electric phenomenon, some rocket stuff here, kind of what all tracers is all about. So go ahead, Dale, with the next thing.
If I can, I'll let you do that. Bring up my don't do this at home thing. Okay, so what we're going to talk about is the magnetic field lines, but first we have a slide that is very important for you people, because even the professionals like Corey and I don't get this right all the time, all right? So the important thing is, the next one please. Don't try this at home, all right? This is not for you to do at home. This is for us to do here where we can kill ourselves and not have to worry about liability somewhere, all right? Graduate students are good. Undergraduate students, we can't harm them too much, but faculty and staff, no problem at all right? So, the magnetic fields, what Corey was talking about, the cusp. If I do this here, if I just put some iron filings around a little magnet, what you can see is those magnetic field lines, but you see at the top and the bottom here, right here. This is the cusp, where the magnetic field lines come around and come into the pole of the magnet, all right? And at the top, it's the same thing, where they're going out and coming around, all right? So that's the cusp. Now, how do we usually tell whether there's a magnetic field around, all right? Anybody want to take a guess what's the common way to detect a magnetic field? Yes? With another magnet, if you're close enough, right? But if you're outside walking around, what's the simplest way that you have that you can tell which direction you're going? A compass, all right? And that's what we have here. I have some compasses here. You can see that these two are pointing to this pole. These two are pointing to this pole, and this happens to be the North Pole up here. But if I move these around, you'll be able to see, they move around with the magnetic field and are always pointing towards the magnetic field strength, the strength of the magnetic field. And in our case, north would be over that way somewhere, okay, if you're outside with your compass right now. But that's our usual way to detect that. It's pretty hard to read a compass on a spacecraft out in space, right? You just don't do that. So what we're going to do is, what's our next one? Copper plate and magnet.
Copper plate, yeah.
So what we're going to do is talk about magnetic fields and how they are used to generate electricity. So I need one volunteer. And Andy, if you would pick 3 other volunteers and get them outfitted with
helmets.
Their helmets and glasses here. Yep. So we need 4 volunteers, actually. So I'm going to have you come up with me right now, and the other 4 I need to be little guys. Little guys. All right? So there's one up here, Andy.
Okay.
One up
We're
here.
going
You
to
can
outfit
come.
the little people with helmets. Okay. If they're a bigger
We need
person,
one
they will
more.
use this helmet.
You need to go with those guys and get outfitted, okay?
You don't get helmets, no. You're grad
Don't
students.
step on
so.
that.
Glasses too.
Don't step on that. Don't step on that. Come this way.
Sorry.
Go around.
Wait,
Go
wait.
around.
Don't forget your
Just
your
step with me.
glasses.
All right.
Need that too.
We'll get this worked out.
Yeah.
All right. So the way that we usually generate electricity in our world on Earth is by just moving a magnet and some copper. Okay. So now, if you would just grab that and lift it about this high and then just drop it. And if you drop it like this, it's even more dramatic, all right? So what's happening? You see that when we drop this magnet on here, it just kind of floats into the plate. It doesn't go clink, clink, clink all the time like a regular magnet does, right? So it just floats into the plate. Now, if you push that over, yeah, we'll do it this way, all right. All right, good. You good at catching?
I think so.
So watch this. When I drop the magnet like this, right, it just falls like normal, like a ball or anything else that you drop, right? But if I drop it off of the plate, whoops, we need to get that. All right, if I drop it off the plate, you see how long it takes to get off of the plate? Okay? It doesn't drop because it doesn't make any difference whether it's dropping or falling away from the copper or towards the copper, or if the copper is moving towards the magnet or away from the magnet. It doesn't make any difference. We're generating electricity when we do that. All we do is move a magnetic field around copper most of the time, all right? Now you have wind in Iowa and you have solar cells that you had playing up there. Those are only about 20% of your electricity generation right now, okay? So making electricity is fairly easy. All you have to do is have a magnetic field and move it through something that has a lot of loose electrons so you can move the electrons around, all right? Give her a big hand. Jeffrey, good well. All right.
This one next.
So the other thing, and you guys can now just sit on that. Just have them sit and grab a handle. Grab a handle. All right. While they're doing that, we're going to come around with this.
Okay. You want me to go cover this one?
No, we're good. Yep. Sit down and you face it this way.
Should we get one more volunteer for this one?
I think we're good.
Okay.
All right. Because I don't want to
Okay.
electrocute anybody for this.
All right.
You want to do this one?
I'll do this one, yeah.
All right.
So we talked about plasma a moment before. Plasma is just charged particles that are moving, basically. They don't have to be moving, but they're essentially charged particles. Like, what's an example of a charged particle that one of you knows about? Yeah. Electron. In fact, that's what we have right here. We have a stream of electrons flowing through this tube. When I turn this on, it lights up. There's a gas inside there. It lights up that gas, and so we can see the path of that stream of particles there. Essentially what we have is visible electricity right there. Now, you can influence that electricity with a magnet, observe, Whoop, whoop. That's the North Pole. Now watch how the South Pole does it. Whoop, whoop.
And then do it
Goes
from
the other way.
side. Do it from the back
Go
side.
from the back side. Whoop. North Pole. South Pole. So we can influence our electricity, our electrons, with a magnet, just like before we were making electricity when Dale was using the magnet in the copper. This is the reverse effect. You're using the electricity to feel the magnet basically right here.
All right, so if you guys would take this table out.
All right. Yep.
Oops, watch out. Sorry.
Sorry.
Got it. Oops.
We're
Other way,
experiencing
other way,
technical
other way,
difficulties.
Other way.
Now we're going the right way.
All right. We're getting
One more time. There we go.
Eventually. There we are.
All right.
Okay. So, like I said, we're going to interspace rockets in this thing because we got to get stuff into space at some point. So what we have is our 3 astronauts right here.
Want to push
All
that
right?
rest of the way there? Thanks.
Corey and I are going to be the retro rockets so that hopefully we won't send our astronauts through that wall over there. That's never a good thing. And what we have here is our fuel. Okay? So our fuel, and we're going to get this out here a little bit. So you guys, be ready and hold on tight because this is going to go like this, all right? And it's going to move you back and forth pretty fast. All right, so our fuel here,
Load up fuel.
and
There you go.
Corey, get up here so that you can
Right.
hold on to these guys and they'll have something
Okay.
to hold on to.
All right.
Okay, so our fuel is what we shoot out the back of the rocket to send the astronauts this way, all right? So it doesn't make any difference whether the fuel is solid pellets or gas or anything like that, as long as it comes out of here at a high enough velocity to send our payload the other way. all right?
Graduate students work really well, actually, as you see.
So our fuel here, and we're going to move this out just a little bit more. All right. So our fuel here, when we dump it out the backside, is going to send our astronauts going this way. And remember, Corey, we're not going to try to stop them until after they go by the computer, okay?
No worries.
All right, so here we go. Corey and I are the retro rockets. The fuel is here. Are you ready? All right, we're going to dump fuel.
Yeah.
Anytime.
All right.
And you can see our astronauts had a real high G going out there when they got started, right? All right. So now we're going to
Gotta get
get
the
this
next table.
platform out of the way. All right, so you guys can come up here, take your stuff off, put it up here on this table. All right. We're going to help you get off of here, okay? Good. All right, very good. You guys, 2 guys, grab a hold of this end right here. Push it over against the wall. And now fold it. And watch it going down, don't break it. All right. And then pick it up and take it down the hallway to the clear to the end. Okay. So is this next?
This is the next one you got listed.
All right.
Meteorites.
So, when we're talking about plasma is nothing more than, you know, on Earth we have an atmosphere that's pretty heavy. I mean, if you run, you can feel the wind trying to blow you back the other way, right? Or you can see the windmills going in Iowa when the air is moving around. That's a real heavy atmosphere. Plasma, on the other hand, is very thin gas that is very highly energetic, can be energized by electric fields, or a magnetic field, or heat. And one of the ways that I can do this is I have your basic microwave oven here, okay? Inside are a whole bunch of little neon light bulbs, all right? Now, if you want to see the plasma inside of a microwave oven, this is what it's going to look like. All right? So this is the plasma inside a microwave oven. You can see that a microwave oven, the standard oven, does not have smooth plasma all the way around it, right? That's why you have to turn the turntable on the food so that they run through all those different hot spots to evenly warm your food, okay? But this is plasma, okay? We're just heating those gas-filled tubes until they glow, all right? So when we're talking about the Earth moving through the plasma coming from the sun or the plasma that surrounds the Earth, this is the kind of thing we're talking about. A very thin gas that is highly energetic, and you see this all the time on other types of space weather that we have. And space weather is not like Iowa weather. You know, the stuff you came in through tonight, the thunderstorms and stuff that are supposed to be rolling through, that's weather, but that's nothing compared to space weather, all right? Space weather, most of you probably figure that deals mainly with rocks, okay? Meteorites and other rocks coming through here, all right? So we have different kinds of space junk that falls into the Earth's atmosphere, glows when it comes through. If it's big enough, it lands and makes a big, big hole, okay? But that is space weather, okay? So, you know, one of the biggest things about space weather that we're concerned about is the fact that, you know, if an asteroid is big enough, it's a planet killer. It will kill everything on this Earth if it strikes and is big enough to create nuclear winter for a couple hundred years, all right? So that's what we're concerned about. When we're talking about space weather and looking out to see what kind of stuff is coming towards the Earth, that's the kind of thing that we are really looking for, is big rocks and junk like that, or comets, big meteorites. But that is a relatively small fraction of the dangers of space weather when it concerns the Earth, all right? So we're going to take this one out, and we have this one coming in. Is this our, which one is unplugged here? Hold on, guys.
Here you go.
Here you go.
Sure, I got this.
So, yep, you're good. You're good. That's good.
Two.
Now, I need one volunteer for this. Well, actually, I need, one volunteer for this one. So who didn't come up yet? Who didn't come up yet? I need some, well, come on up. Because I need somebody who can hold a magnet and not let it drop into my glass tube, okay? All right, so the plasma that we're talking about. If we turn on my power supply here, you're all good, you're all good, you're all good. Don't worry, don't worry. If we turn on my power supply here and we turn down the lights a little bit, and we'll try 3. There. All right? Just a second. I let them take too many things out.
Okay, sorry.
Forgot to keep my magnet. You know, it's one of those things you get moving stuff out so fast you forget what you have left in the room. Okay, so you get to come over here. As you can see, I have my power supply going here, but my gas-filled tube is not lighting up, all right? Because the atmosphere in this is too heavy. It's like it's regular Earth normal right now, okay? 15 pounds per square inch. We can't get electricity run through this thing. But if I turn on my vacuum pump, oops. Now we have made a plasma because we have taken the air enough out of this tube that now we can get electrical conduction through this gas. If you want to turn down all the lights there, that'd be fine. Just off. Yep. All right. And now that cusp that we were talking about in the plasma, or where we usually talk about the northern lights or the southern lights, that's the particles coming into that cusp and they're getting heated or electrified enough to glow, okay? That's what you're going to do here. I want you to hold that magnet right over there. All right, you can see how the plasma reacts to that magnet, and you can come over to this side so that the people over there, your professor for a minute, okay? You can see how the plasma reacts to that. And that little dip in the plasma, that's your cusp, okay? Where the particles are moving towards or away from that magnetic field that she's holding over there, all right? And you can go back over there and do the same thing. And you can turn the magnet over. I mean, the plasma is smart enough to know that, you know, what magnet or what pole of the magnet it's looking at, so it doesn't worry about anything like that, okay? But that is the cusp, that dip in the plasma that's coming into the magnetic field. That's what we're talking about when we're talking about space weather, plasma. The Earth is moving through the plasma. So the Earth is the magnet. The plasma is the stuff coming from the sun and that surrounds the Earth as it's moving around the sun. And so that is the interaction that tracers spacecraft are looking for. Because we know that there's a big interaction, but we don't know how that interaction takes place, or how difficult or how easy it takes place, and what the magnitude is, how big that effect can be. We've never experienced that except for twice in our lifetime right now, so pretty much. Okay, so I'm going to let you turn back the lights, Corey. I'm going to turn this off. And we're going to have all the lights back on, and give my volunteer a big hand. Just all right. So one thing about the plasma is I've already told you that it can be electrified to carry a current. It can be heated up to glow. The magnetic field can affect that. If it's an oscillating magnetic field, like a radio wave or something like that, that can affect it also. So one of the easiest ways we're going to start off with communication is the one that Corey's going to do for you.
Okay, we'll go with you. And then we need a youngster. Who hasn't done this yet? Have you done this? All right, why don't you come
All right, I'll get this going.
Okay.
Sorry.
You come over here. I talked about the magnetic wind, so to speak, the magnetic field that the Earth creates, the Sun creates. They do so, again, by charged particles moving. Electricity creates magnetism.
I want you to hold this one.
We're going to do that
just
here
like that.
with a old-fashioned, it's called a CD player. Who remembers what the heck that thing means?
Hold it.
Okay,
like
good. All right. Anyway,
And
for the
hold
younger
this one in the
folks,
other
it's
hand.
something that
Very
plays
good.
music. But right now, our CD player is just making electricity. It's not connected to a speaker, not yet. But the electricity that it will create is going to run around this copper wire here. It's going to create that magnetic field, that magnetic sort of wind. Now that wind can be caught over here by this copper wire that's connected to the speaker. And if we hold them just right, we should be able to transmit the magnetic wind from this one to this one and hear the sound here.
This is a poor magnetic wind, so they must get
playing?
much closer together
You
here.
get closer. Notice they don't have to touch though. I want you to turn it like this. That's not working as well. Turn it back the way you had it. Play around with them a little bit, see if you can get it
closer.
louder or
You can get
softer,
closer.
depending on different things.
So if you
Move them back and forth. a
if you
little bit,
move
make
this
like
way.
there you go. You can dance a little with the music, go back and forth. Now we want it really soft, so walk away from each other.
all right.
Okay, now get louder again, come closer. And softer, back. And louder, back.
All right. And if we wanted to, you know, we could take both of these and see the song in her head. Oh, heck, it's the same music I like, you know, so, you know. But the magnetic field goes right through you. You don't feel that at all. So, but we do have visible outlets for that, or visible radiation that we see in the northern lights, the southern lights, all of that is radiation just like this, only it's a little bit more complicated in how it's produced and how it is sustained and stuff like that. Give our two volunteers a great hand.
That one, yeah.
All right, where are we at?
Take this out.
I don't have any. I just want to put it open. That's fine. That's what Sal does.
All right.
I don't need them.
Now, what I had Corey do here was a simple way of communicating on Earth, where we just have some copper wire that we're running electricity through, creating a magnetic field. We can pick it up with an antenna. Basically, it's a radio transmitter and the listener at home type situation for that. Here, it's a little bit more complicated. And if we could, oops, there. If we could turn off the lights, it'd be fine. There you go. This is the plasma that all of you guys have seen at one time or another. A plasma ball, you know, you can do all kinds of things by putting your hand on it and the lightning comes to you. But this is a plasma. It's a very special combination of gases that they have. So you have some red or pink and you have some blue and you have some other things, all driven by a high-frequency Tesla coil at the bottom. All right? Some of these you can make pulse to sound and stuff like that because the sound coming into the ball actually creates different kinds of energies on the inside. But that is a plasma that can carry a current. All right? So the electricity that you see here is actually gas that has electricity or current running through it and doing some work. In my case, my hand will get hot if I leave it there too long, but the plasma ball will just go like that forever, okay? On the other hand, you know, around here anyway, we like to make our plasma do some work other than just make the nice northern lights. And so here we have a plasma speaker. Because the plasma, like I said, if you can run electricity through it, you can modulate that electricity and create a sound, all right? And Corey's going to do that.
Okay. Ready?
All right? So we have, you see our plasma up here, all right? I can get my hand up there, you can see that. But that is our plasma.
I think it turned off.
Yeah, that's all right. All right? But notice, you know, I don't have to be connected to the plasma to make anything work. All right? I can come over to this one and do the same thing. All right? So the plasma, as long as I have it in a conductive state, I can make it glow by moving something in it or by creating a pulse of electricity in it or doing anything like that. So plasma is really a kind of a cool thing. Now, for all of you who are old enough before LED lights came around, you know, the fluorescent lights were nothing but plasma tubes, okay? So you turn on the fluorescent light, it started to glow on the inside, it bounced against that white coating on the inside of the tube, and you got nice bright white lights coming out of it, all right? Those were actually plasma tubes. But a plasma speaker like this, we can actually make it oscillate so that the plasma does some really cool things. All right.
Go ahead and take that out.
Now, for, well, not quite my generation, because I was born before 1958. All right. So my generation started with no spacecraft in space around the Earth. All right. However, nowadays we have 15,000 spacecraft around the Earth at any one time, and we're sending more up all the time. The problem is, as I said, space weather. All right. What happens if the sun burps and gives off a plasma ball or a plasma arc, or burps some particles out, or even if you just have a high sunspot activity cycle in the sun, right? What happens? Yes?
Aurora borealis.
Aurora borealis, we've seen those coming all the way down to Florida the last couple years, right? Because they're a lot of energetic particles coming off the sun. The arcs and the coronal discharges and stuff like that are coming through pretty fast and furious right now, all right? But what happens if one of those happens to be very violent and directed towards the path of the Earth, all right? Well, spacecraft do not like that, all right? So one of the things to talk about, I guess, is everybody likes these, right? And you like it that you don't have to read a map anymore. You can just hit Google Maps and it will tell you where to go and where to turn and all that stuff, right? And would you be able to survive if your spacecraft that is telling you all of that stuff is suddenly dead? You know, that's going to be back to my generation where you have no longer portable phone, but you have landlines and you have no computers anymore. You know, you're doing everything with a calculator that goes like this all the time. All right? So you have all of those things that you can have to worry about when we put stuff into space. And the big thing about this, the problem is that most of the early spacecraft was not designed to withstand any kind of bad things happening to them from the sun, okay? Or if they crashed into the Earth either. So I need 2 volunteers in this one, and we need to outfit you.
Why don't you go pick them out?
Because we're going to show you what happens when bad things happen to your spacecraft.
To the spacecraft, not the astronauts coming
Yeah,
up, of course.
to the spacecraft.
Yeah.
So like your, your GPS satellite, your satellite TV satellites, your phone satellites, everything like that. Bad things happen when electrical charged particles come into the Earth. A long time ago, like 20, 25 years ago, the power system or the electrical grid in Canada went down because there was an electrical discharge from the sun. And all the copper wires that were run around distributing power all over Canada picked up that charge, had a blackout, okay? They had to reset everything and re-examine a couple relays and stuff like that to get them back up and running. But bad things happen. You get to go over here and you get to have these on. All right, right over here. And if you could hold on to that balloon, Corey. All right, so here's what's going to happen. We're going to back this up so that these guys in the front are kind of safe. But if you have a big electrical discharge in your spacecraft, this is what's going to happen. All right, you need to come back over here. See this big switch? Mm-hmm. Flip it on. All right? That wasn't very spectacular, was it? We'll try this. We always go for 2 shots. That was better, right? But that's what happens when you have a high energy electrical discharge that happens inside your spacecraft. All right? Everything just burns up. All right, give our volunteer a big hand. He did a great job. Didn't get too scared. All right, now that was just a resistor. So you know your resistor board, but your boards nowadays have resistors, capacitors, IC chips, and everything else on them. And that's what this one is going to be. This is the same type of thing. What happens when you get a big electrical discharge? Flip that switch. All right. So once that happens, your spacecraft is non-operational, right? I don't have to tell you that. So that is the kind of thing that we need to be able to predict if that's going to happen. We can shut the spacecraft off, or we can protect the spacecraft by adding some other components and insulation to it. But we have to know when that's coming, and if it's coming our way, and how big it's going to be and stuff like that. That's what Tracers is trying to figure out for us. Because we know we have the northern lights, all right? We just don't know how they're generated most of the time, and we don't really have a good prediction about how big they're going to be and how far they're going to be, how far down we can see them, which means that, you know, they're huge if you can see them down in Florida, right? So that is the problem with tracers. We don't know a lot of things, a lot of times, how those things are going to come about. All right, give our other volunteer up here a big hand. You can put your glasses up here. All right, I'm going to keep these glasses. All right, so now we need another volunteer that can ride a bike. No, you've already been up here. You were an astronaut. Can ride a bike? Who do we got? We got one up there? Well, come on down. Don't be shy. You know, we can only kill you once here. All right. So again, our rocket thing. Talking about our spacecraft. We need to have you have those on. We'll pull that. We'll pull this. We'll make it light so it goes real fast. All right. All right, now you need to sit up here.
Okay.
This bike has no brake here. You don't need to pedal, but you just put your feet up on the pedals. All right. It has no brake except for this one right here. All right. So going backwards isn't going to help you any. All right. So what you got to do is steer with your left hand, and with your right hand, reach behind you. Reach. No. Oh, sorry.
Wait.
Steer with your right hand. Put it on the brake, right?
Okay.
With your left hand, you're going to squeeze these two things together, okay? And you're going to hold that down until you get to me, all right? And then you're going to, when you get to me, then you get to hit the brake before you hit the wall, okay? All right. Anytime. All right. So I didn't tell you how noisy that was going to be, right? I also didn't tell her how cold that was going to be on her back from the backwash off the wall. But that is exactly what a rocket does. Most of the time it's hot, compressed gas coming out very fast this direction, sending our astronauts or our spacecraft off in that direction. All right? So that's just one other example of a rocket that we like doing all the time because everybody likes that one. Big clouds and everything. All right, what do we got? Balloons are next?
Yeah.
So,
Which is this okay here, or?
yep, that's okay right there. It'll take me a couple seconds to get this one up and running. Oops, I gotta get out and around here. All right, plug that back up. So, how do we generate the high pressure, fast moving gas? All right, in our spacecraft. Anybody want to shout out an answer? You know, we got a lot of space physicists here, but we're not going to let them answer tonight. Okay? Anybody know how we usually get our spacecraft into space? What kind of gas we are able to generate and how we do it? Yes? Hydrogen? It works. And it works very well. But you got to have something else to go with it, right? I mean, you can burn hydrogen, but it doesn't burn fast, right? What else do you got to have with your hydrogen? Yes?
Oxygen.
There you go. And what is the reaction? Hydrogen plus oxygen equals water. There you go. All right. I have to do this one because we use this on a 10-foot pole. So literally a 10-foot pole. Okay. So what I have in this balloon over here is hydrogen. And the oxygen that we need to make our water is going to come from the atmosphere that you're sitting in right now, okay? And it's going to swirl around here and mix with the hydrogen, and you're going to see that swirling motion. This is a very slow chemical reaction. This is not how we get most spacecraft into space, all right? So here we go. Corey, if you would hit all the lights, please, or Cole. All right, so here we go. This is what hydrogen plus oxygen equals water. All right? I told you it was a slow reaction. Takes a long time. So the amount of water that we made just now is about the same amount that you breathe out every time you exhale. So if you just go, and that cloud that you see when it's 20 below outside, that's about how much water we made. This one, on the other hand, is going to be more violent. Because we have the hydrogen and the oxygen mixed together inside here already, okay? So, everybody needs to cover your ears and open your mouth. If you don't like loud noises, go in the back. You'll be able to tell when this is over. The shock wave will pass through you. All right. So make sure you cover your ears, open your mouth. Here we go. All right. So that was more the reaction of when we send a spacecraft into space. Because for all of you who are old enough like me to remember when the space shuttle used to be going up into space, that big red tank was filled with liquid hydrogen, liquid oxygen. You'd run it through a big pump and shoot it out the engine and light it off. And, you know, the explosion going that way would shoot the rocket up that way. So that is one of the main reactions we have, is just to make water to get stuff into space. We have other things too. We can do solid rocket boosters and stuff like that, but basically what those are just solid fuel pellets that have a lot of oxygen around them so that you still have a lot of gas going out one way. Yes?
Why did you have a solar balance?
So that you could equalize, you felt the shock wave. Even if you didn't hear this thing, if you had your ears closed hard enough, but the shock wave going through here creates imbalance on both sides of your ears. So if you open your mouth a little bit, the balance on both sides of the eardrum is a little bit better off. Okay? So that's why I said open your mouth, all right? So, you know, cover your ears, open your mouth. The shock wave is what you got to watch out for on this type of thing. All right. The last, well, almost the last things.
The penultimate.
And then don't leave because we still have prizes to give away. All right. If I can get this going without destroying the apparatus. So, the demonstration that we're going to have here is more about what the aurora is going to look like. Okay, when we look at the aurora, especially if we look at the north and south poles from space, we don't see the aurora, you know, like we see it down here on Earth. What we see is like a glowing ring around the north and the south poles. All right? And that is kind of what we're going to do here. So, Corey, if you could hit my lights. If I tickle this, you can see I have my plasma here. If I put my hand up here, you can see the beads, but here is our auroral arc, or the auroral cusp, where the particles are falling into the magnetic field. Now, our magnetic field is being generated down here by these little wires, okay? But this is kind of like the auroral ring at the north or the south pole. This is what it would kind of look like. It oscillates just like this. It's not stable. It's not, it goes in and out, and it goes up and down, and it oscillates back and forth. So this is a pretty fair example of that, all right? Now, I can play with this a little bit and get it down so that, if I get it down far enough. The other nice thing is, if I put my hand up here, you see that the plasma is not the arc like you saw with my plasma globe, all right? It's more like a string of pearls type thing, all right? Which is more like particles falling into our magnetic field lines of the Earth, because, they are like galloping in, bunching into other ones, and then there'll be another pause, and then there'll be a bunch more that bunch together. So it's like cars going down the highway, right? If one breaks in the front of you, then you get a whole bunch of them bunching up behind you and stuff like that. That's kind of like what is happening in real life on the poles, okay? With the plasma that we're going through and the magnetic field of the Earth, creating these kinds of things. So if we get this up going, and we're going to have a couple of these up here so that you guys can come up here and play with these afterwards. The other thing I want to draw attention to is the one that we've had going up here. I said that there's particles and stuff coming from outer space, and from our sun in particular. We're near enough to that, but there's other particles coming from outer space. And all of those white streaks that you see going through the kind of like the fog background that you see there, all those white streaks are cosmic rays. There are thousands of cosmic rays going through you every second, all right? And it's one of the primary causes of aging of your skin. You just can't get away from it, all right? So there's nothing on our Earth that we're going to be able to do about premature aging of stuff, because we have this kind of stuff hitting us all the time, all right? But there's particles there. If I really wanted to show you some really good stuff, we'll try this. And now what you should be able to see is when that quiets down a little bit, you see all the white streaks coming off of that? Those are radioactive particles that are decaying and going out into the fog there, and they leave trails. They leave those white trails coming off of there whenever there's a decay of radioactive particles. So that's one of the things that we have on Earth all the time. We're protected from a lot of that by the magnetic field of the Earth and the Van Allen belts, all right? But the magnetic field takes care of a lot of that. But if the sun is energetic enough, even the magnetic field in the front, where you saw in that front picture, where it's kind of compressed on this side, goes out this way on the back side. Well, if we compress that front side enough, we could be in trouble, and have a few difficulties as far as radiation goes. But right now, we're protected from it, so it's not something that we really worry about too much, but it has happened in the past. So we need to be able to predict how that's going to happen in the future. That's what TRACERS is about, okay? So, well, Corey, we're going to take this one back over here.
Okay.
Now, I would ask for volunteers for this last one. Just take it right back over there. And like I said, you guys can come up and touch this one and play with it, and we'll get a couple of the other things out in the back that you can play with. All those plasma globes out back you can touch. But this one is one that we got to have the big guys help us with. And if you could get all of this stuff off the bench here so we don't blow it off onto the floor. For now. All right, so I need three gentlemen here, three big guys, Sal, Cole, and come on up. All right. And you two, I want out front. And you'll need this. You'll need this. So Sal, go out front. I got this one. You got that one. All right. So, this is my rocket engine. All right. It's called a pulse jet engine. It's what we use to send a lot of the early spacecraft into space or to do a lot of the rocket testing. For those of you who are old enough to remember World War II, this was the V-1 and V-2 rocket, how they were sent and launched onto England. Okay, so what we have here is a chamber where we're going to ignite some fuel. It's going to blow out the back. When it blows out the back, it's going to suck in more fuel to the chamber, and that's going to light and go out the back. So it's going to be really loud, and it's going to be a very rapid pulse, like real fast, okay? Things are going to get really, really hot. But I need to have you guys help because, get your torch. I need you to just hold this right here and make a brighter red spot as you can get. And then when I get the engine started, you guys can shut off your torches and move out of the way here. But just like he's doing, a big bright red spot, okay? This will be very loud, but it's not started yet. All right, you got it? Let's try this. All right, notice on this engine, there's no shut-off switch. It just goes until it runs out of fuel, all right? Because once you get it started, there's no shutting that thing off. All right. So now, everybody has their ticket. And Andy, do you have the ticket thingy? There we go. All right. So I have some door prizes. Hopefully some people will get some. We're going to let Corey pick. Andy can shake. We just need to read the last three numbers.
The lucky winner is 098
Who has
506.
506, all right.
Do you want to select the next one?
So what that means is that one of you two girls is going to get something when you get home, okay? All right,
Next one?
you get first
Oh.
pick.
Wow, fun.
Okay, all right, next number.
All right.
Just
Andy,
the last three numbers, that's all we need.
That was like 8 tickets.
521.
All right, come on up. So these are swing toys that go back and forth and do stuff. This one goes
Laksha.
round and round.
You want to go next?
All right,
It's like 4 tickets.
next one.
All right.
515.
All right. You get a toy! Here, I'll even bring this to you. Which one do you want? Which one do you want? I tell you, you want that one. All right. That's the one you want. All right.
Another?
Yep. 3 more.
Okay. 529.
You can pick any one you want.
Yes, sir.
All right.
Show the people what you win. You? Okay.
Why are you putting it so close?
517.
All right.
There we go. Sal, I think you get to go. I think you're the last one.
Either one you want. Yep, that's fine.
One more, right?
Very good.
Last. Oop.
Uh-oh.
Party foul. We'll put them back in, and then we'll pick. Okay. Presto, changeo, sallow.
$556.
Yay! Lid, please. Oh, just the lid. We'll put the lid back on.
Okay. Now, we'll get that taken care of. Oh, all right. So good. So with that, that's the end
It's
of
like
our
the perfect
program.
timing. That's like
you
the
can
end of
come
the
up
show.
and take a good look at that one if you want to. You can take a good look at the cloud chamber. You can come up and look at some other stuff, but if you have questions, Corey and I will take care of those, or Andy. Andy is there. You get Andy, okay? So we should be able to answer most all of your questions. Make sure you get plenty of
Try.